to the wonders of the Northern Lights. I'm delighted to welcome Dr Carolin Crawford from the Institute of Astronomy here at Cambridge. The event is hosted this evening by our tour operator Hurtigruten, who has been taking Oxford and Cambridge alumni to Norway for the past 10 years. And on that note, I'd like to hand over to Russell Cox from Hurtigruten.
Thank you very much, Claire, for that introduction. Good evening, everybody. It's a shame I can't, you can't hear me.
I can.
Oh, fab. I say it's not showing that I'm muted. Good evening, everyone. The joys of technology. Perfect, you can hear me. Thank you for those comments. Welcome to our presentation evening. As Claire has rightly said, I'm Russell from Hurtigruten Group. My job is to talk about all things Hurtigruten and basically predominantly sell holidays. Now, clearly, the point of today's talk is not to do lots of that, and that's not the intention. I know you're all here to hear and to listen to the wonderful work that Dr Carolin does and hear about the solar system, and I'm particularly excited to hear everything that she's going to cover in her presentation today. So I just wanted to say a couple of quick things about our business, just so that you're aware of those, and then I'll pass it over to Dr. Carolin, of course. So Hurtigruten Group has two brands. We have Hurtigruten Expeditions, and then we have Hurtigruten Norwegian Coastal Express. And I know many of you have already travelled with us because we've been working with the travel programme with the alumni for such a long time. So for those of you who have travelled with us, thank you very much for your business. For those of you who haven't or would like to consider it, then we would love to see you on board with us very, very soon. For those of you who don't know Hurtigruten Group at all, we are the world's leading adventure travel group, and we offer unique small ship land-based adventure holidays pole to pole. So we're a cruise line. We take our guests to the most spectacular areas of the planet, and we offer a mix of pristine wilderness visits, and we take you to see local communities. Hurtigruten Group is revolutionising the travel industry approach to sustainability. It's something that's really important to us, allowing us to offer authentic local experiences while leaving the most smallest footprint possible. Of course, also our commitment to safety is incredibly important, and that matches our absolute passion for exploration. We've got a fabulous trip lined up that Dr. Carolin will be hosting and escorting, which is departing in November 2022. And Claire and the team will be able to provide you with lots of information on that. Not surprising, it's a Northern Lights themed sailing. So really ties in brilliantly well with the work that Carolin does, and she will really be able to bring the Northern Lights experience to life for you. So that is really, really a nice thing to be involved in and to experience. I've seen it many times and it is incredible if you haven't, so I'd really encourage you to do that. At the end of the talk, we're going to host a question and answer session. So if there's any questions that you have for myself or for Dr. Carolin, then please just write those in the notes and I'll follow those while Dr. Carolin's doing her talk, and we'll cover those off at the end. But without further ado, I'll now pass you over to Dr. Carolin so you can get involved in all the interesting stuff clearly that she's going to talk to us about. So looking forward to that. Over to you, Dr. Camb. Thank you.
Thank you very much, Russell. Right, so here comes the technology bit where I try and share the right bit of the screen. And then right, can you see that as a slideshow?
Yes, Dr. Carolin, just we could see it in the presentation screen rather than the full size.
Okay, right, just bear with me then, because that's, as usual, that's what worked before. There we are. Is that better?
Perfect.
Okay, well, welcome everyone. Delighted to speak to you. As Russell says, I'm supposed to be the host on next year's cruise to see the Northern Lights. And I will in fact be talking about a whole range of astronomy and cosmology during that trip. But to give you a taster for the Northern Lights, I'm going to talk this evening about the one area where space really impacts on our Earth, right at the top of the atmosphere, the boundary between the solar system and the Earth's magnetosphere, and gives us these fantastic light shows that if you're ever lucky enough to have seen, you know that these videos that I'm showing you at the minute are a poor representation of the true experience. So the Northern Lights can take many kind of manifestations. It could be a sort of low glow down in the north. It could be snaking ribbons of light across the sky. It could be arcs or coloured green curtains waving, as you can see in the video at the minute. And these will often disappear and return maybe several times in a night. And the Northern Lights are best seen around sort of 2 to 3 hours around midnight. And it's ideal if you're away from light pollution. Ideally, you'll have a moonless night as well. And the main stumbling block is the weather. You need clear weather because, as you're going to hear, the Northern Lights occur sort of 80 to 250 kilometres up from Earth at altitudes.
Dr. Carolin, sorry to interrupt you. What we can see on our screens is a very minimalised version of your presentation.
Oh, okay.
On your laptop, are you viewing it in the full screen?
I am. So how do we fix that?
How's that? Is that, I now have you as full screen on mine.
Okay, do you have?
Yes, everybody's now saying that's okay. So beg your pardon, if you could just put it back as you had it.
Like that?
Perfect. Yeah, apologies for that.
Okay, thanks for letting us know, everyone. Sorry, we're struggling with technology a bit. But okay, so you're beginning to see some of the videos that you've missed. But the main thing I was saying is that they're best seen somewhere moonless, away from light pollution, ideally around midnight, and you need clear weather because Northern Lights are happening at the top of our atmosphere. You're talking about 100, 200 kilometres altitude, and that's way above even the highest clouds. And they're best seen in that they're the finest apparitions and the most frequent at high latitudes. And here's just, if you like, it's a probability map for this evening about where one might see aurora. And as you'll see, high latitudes are best, ideally within the Arctic Circle. I'll talk about this map and this sort of probability that, you know, seeing aurora later, but they're best at high latitudes. And the final thing that determines how good the aurora are, where you see them, how bright they are, depends on the activity of the sun. So despite being 150 million kilometers away, the sun is a crucial component of us seeing the aurora. So obviously, aurora have been seen for thousands of years, marveled at thousands of years, and stories about the Northern Lights have been embedded in folklore and mythology of many cultures, particularly those in the north. And they tend to be associated with ancestors, restless spirits, perhaps even with premature death. So one example is the Greenland Inuit saw the Northern Lights as representing the souls of, say, stillborn children. Here's just a pictorial representation of that idea where they're rather bizarrely playing sort of football with the walrus skull there. And you have the Inuit of Alaska who saw them as the dancing souls of their favourite animals. So you've got caribou and seals and walruses and whales. The Vikings associated them with reflections of the shields from the Valkyrie who came to collect the slain heroes from the battlefield, the heroes that Odin had chosen to go and accompany him in Valhalla. You've got many myths and oral legends within North American indigenous tribes, again associating them with the spirits of recently departed relatives, or even One example is very imaginative ones, where there'd be light from the cooking fires that northern warriors are boiling up and simmering their enemies in a giant cooking pot. So many, many different stories about the Northern Lights. Within Europe, you also have a variety. You've got, they're known as the merry dancers in Scotland. In Denmark, there's this legend of a flock of swans who flew too far north and got trapped in the ice. And whenever they flap their wings, it causes reflections high in the sky. Or one of my favorites is from Finland, where you have an Arctic fox up north, and they the fox whisks her tail through the ice, and the ice crystals fly up into the sky where they reflect the light. So there are many, many different stories, mostly, as I say, from northern cultures. In southern Europe, they're very rarely seen, again, for reasons that we'll talk about in a bit. So at low latitudes, you're lucky if you maybe see it maybe once, twice in your lifetime from your home. And you need particularly intense solar activity for aurora to get down to such low latitudes. But again, they are seen, and the myths tend to be associated with disaster. That's because southern aurora, or the bit of the aurora you see from the south, tend to be red in colour, and red is associated with the idea of spilling blood. And so they're usually taken as an omen. Now, in terms of historical rather than folklore records of the Northern Lights, the first reliable record we have dates back to about 2,500 years ago from the Babylonians, where there's one of the clay tablets which records an unusual red glow to the north. And there is again this idea of the red glow comes back up with Tiberius, who apparently saw a red aurora in the sky and was so convinced that this was the port of Ostia on fire, being looted, that he sent his army to go and rescue the town. And even more recently, back in 1938, fire brigades were dispatched to Windsor Castle because there was a red aurora in the sky, and it was thought the only possible explanation of this red light was that perhaps Windsor Castle was on fire. So it's very unusual, and when it's seen, people didn't really know what they were looking at. It was Galileo that first coined the term aurora borealis, effectively sort of dawn of the north. But like other astronomers and scientists of the Renaissance, he didn't have a clear idea yet about what they were. There were various ideas. They could be solar rays reflected perhaps from northern glaciers, or perhaps ice crystals, ice particles high in the atmosphere. Or there were other ideas that it could be gases and vapors combusting high in the atmosphere. And it was only really in the early 18th century that Sir Edmund Halley made the observation that linked aurora to the Earth's magnetic field. And he was lucky enough to see a spectacular aurora all across Europe in 1716. And he observed that the rays, the way the light followed down in rays, that these all ran parallel to the magnetic field of the Earth. And they were sort of pointing towards the geomagnetic north rather than the geographic north. So he came up with the connection to the Earth's magnetic field. This was later confirmed the next century in 1859, when there was a severe geomagnetic storm. This is known as the Carrington event. And here's a picture by Frank Church, which we think was inspired by this event, where one of the most severe geomagnetic storms on record rattled the whole of the Earth's magnetosphere. And it was associated with aurorae down at low latitudes, down in Cuba and Hawaii, bright enough apparently to read a newspaper by. And interestingly, this event also gave us the first connection to the sun creating aurora on the Earth, in that preceding the aurora, the John Carrington observed a bright flash of visible light on the sun, and 17 hours later, this geomagnetic storm arrived, rattled the magnetosphere, came up with these fantastic displays of the northern lights. So we start having this idea of the association of the lights with the Earth's magnetic field and with things happening on the sun. You start to get more scientific approach with certainly particularly Norwegian scientists, where they would collate observations from sea captains and look at the distribution of the aurora and, you know, prove that they sort of followed a ring around the magnetic North Pole. They analysed the spectrum of the light and showed it was completely different from the nature of sunlight. It wasn't simply reflected light from the ice or ice crystals. It wasn't reflected sunlight. And they also measured the altitude, and they did this by triangulation, where two observers look at the same aurorae. They each measure the angle to the top and the bottom, and you get an idea of where they are in terms of altitude. And from this triangulation, they showed that they're above 100 kilometers, typically 100 to 200 kilometers altitude. They're not associated with weather. It's not a weather phenomenon. It's something happening high in the atmosphere. And of course, today, we can see this directly from the International Space Station. This flies at a height of about 400 kilometers above the Earth's surface. And there are some beautiful images and movies you can see, like the one I'm showing you now, taken by astronauts above the International Space Station, showing the top of the atmosphere and how the northern lights are associated with just the very top layers of the atmosphere. And you can see there's the green glow topped with some red, and you also get this striation, the rays within the structures within the aurorae. In terms of science, it starts to all come together by about the turn of the 20th century. And you have the Norwegian scientist Christian Birkeland, who has the idea that it's a stream of charged particles from the sun that ignite the aurora. And he tested this in the lab by making artificial aurora. He had a stream of electrons which were channeled to an Earth, which he mocked up as a magnetized sphere. And what he was able to show was, as the stream of charged particles hit the sphere, they got channeled down the lines of the magnetic field. And when he painted this sort of mock Earth with fluorescent paint, they came up as deliberately sort of two rings around the north and south magnetic poles. So this is again beginning to show us how the northern lights are formed. So how are they formed, and what is the connection to the sun, as I say, 150 million kilometers away? Well, to explain this, we need to talk a little bit more about the sun and what I mean by solar activity and how we could influence the northern lights. So when you look at the surface of the sun, it's just an enormous ball of plasma. The surface is at about just short of 6,000 degrees K. And it is moving all the time. You have rivers of plasma, thousands of kilometers wide, that rise up, cool, and fall, and rise up, cool, and fall. The whole surface of the sun is churning continually. And so you've got these rivers of plasma, and at the surface, there is a constant flow of charged particles, you know, a few hundred kilometers per second from the surface of the sun. And this is known as the solar wind, and that is continual. It goes on all the time. It propels charged particles out way beyond the sun, right out into the solar system and into the realm of interplanetary space between all the planets. And when that stream of charged particles coincides with the magnetosphere of a planet, those charged particles get directed down into the atmosphere, where they collide with atoms and molecules to produce aurora. But on its own, the solar wind, even though it's going on all the time, isn't really enough to produce the fantastic aurora that we see. You need events which give just that bit more energy to the particles, the extra oomph and acceleration. And this comes from magnetically active regions on the sun. Now, we know where these are. Oh, okay, I'll just show you this movie. Just bear with me. I want to get it to start. This just gives you an idea of the solar wind is going on all the time, but every so often the sun will give off much larger gusts of plasma. Now, the active regions on the sun are marked by sunspots, and they're dark because the surface of the sun is a couple of thousand degrees cooler there, so it appears black compared to the glow of the rest of the disk. And it's cool because there are strong magnetic fields that are pushing out from the interior of the sun out of the surface, and they're inhibiting that flow of plasma. And so the surface of the, because it's preventing that upwelling, it's keeping the region of the intense magnetic field is kept cooler and appears black. But at the regions of these sunspots, where you have these strong magnetic fields bursting out of the sun, the magnetic field will pull plasma out. And we form, this is just a picture of a sunspot. To be clear, these are thousands of kilometers across. One sunspot can be several dozen times the size of the Earth. And the magnetic field within the sunspot and around the sunspot can be over 10,000 times the strength of the magnetic field of the Earth. And the magnetic field lines pull out the plasma. It can be billions of tons of plasma into large structures called prominences. Here again is plasma coming out of the sunspot, just to give you an idea of scale. Here is the Earth in comparison. It's very easy to forget how big the sun is sometimes, so I hope that rams the point home. And what we're particularly interested in is these prominences. Here's one that is tied to the Earth, to the sun, the surface of the sun. This is 30 seconds worth, comes from about 3 hours worth of observation. So despite these prominences being several times the size of Earth, they will evolve and change on a timescale of tens of minutes. There's a lot of energy involved in this material. Now, what is interesting is when these prominences are so strong that you get some, the magnetic field is sort of tangled and knotted up. So imagine you're sort of twisting up an elastic band or something, and you let it go, and the magnetic field lines reconnect, and you suddenly release a lot of energy. When that happens, you can catapult the plasma that's entrained in the magnetic fields out into space. So here is a prominence, and here's just a view of a similar prominence, where in the top right, you can see it has just sort of propelled this material out into space. And the material, when I keep saying material, we're talking about charged particles, hot charged particles with an associated magnetic field. So this happens when one of these magnetic fields twists and unknots and releases this energy. It can heat the plasma up to tens of millions of degrees almost instantly. So this is just the strong magnetic field that's doing the work. This manifests itself as a flare, which is usually seen in X-ray or UV light. Here you can see this false color image because this is an X-ray movie, but it shows you material being blasted off the surface of the sun. And coincident with that is this bright X-ray flare. I talked about the Carrington event back in 1859, where John Carrington saw a bright white light flare in the sun. Well, that was one of these explosions on the surface. Now, the light from the sun takes about 8.5 minutes to reach us. And that gives us the notice that one of these huge bubbles of plasma has been released from the sun. And if that is directed towards us, if it's on the face of the sun towards us, then it will impact on Earth. Most of these flares will release bubbles of plasma that are shot out any which way into the solar system. It just gets interesting when they come near to Earth. So to remind you about Earth's magnetic field, when it emerges from the surface of the Earth, it's like your standard bow magnet. It's got a north pole and a south pole. And the whole of the magnetic field of the Earth extends way out into space, far beyond the Earth's atmosphere. And it forms something that's known as the magnetosphere. And where the solar wind, that's a steady stream of charged particles that comes from the scene, comes against the magnetosphere, it compresses it. So our magnetosphere is always slightly compressed on the side of the Earth towards the sun, and then you've got this long tail on the other side away from the sun. So when you have an ejection of material from the sun, and this is happening on all scales, yeah, it doesn't have to be a major event, but you have a bubble of tens of billions of tons of plasma and its associated magnetic field. When that is ejected and it reaches the Earth, especially if magnetic field lines are oriented the other way, again, you get this reconnection, you get lots of energy, and that energy accelerates the particles in the plasma so that they spiral down the magnetic field lines in our magnetosphere, and those funnel them down into the atmosphere where they collide with atoms and molecules of our air, oxygen and nitrogen. What is happening is that as these particles come down into our atmosphere, they physically collide with atoms and molecules, and they transfer that energy that they've got into the atoms. And the atoms can store this temporarily before it releases that energy as a photon of light. And this happens most often where the magnetic field is most concentrated, and that happens to be where the magnetic field lines are closest, which, if you've ever seen the field lines around a bar magnet, are concentrated around the poles. And so this is why they're associated with the North and South poles, and indeed the geomagnetic North Pole rather than the geographic North Pole. I talked about this footprint. These are just maps showing you the northern auroral oval and the south aurora, I can never say it's auroral oval. And these are predictions, and these run all the time. The one that I showed you earlier was the one for this evening. And these predictions are done from satellites that are observing the sun all the time and are making predictions about when there may be a blast of solar plasma or the strength of the solar plasma that hits the Earth. So again, it depends on the activity of the sun, determines the predictions for how strong the aurora will be and where they'll be. So here you can see they're concentrated around the North and the South poles. And these are relatively quiescent maps when the sun is not particularly strong. But these aurora ovals shift and change all the time. If it's quiescent, it's at high latitudes, but in strong geomagnetic storms caused by solar activities, the probability will increase and the oval will expand to more southerly latitudes. So these are quiescent. Here's an image of when a storm was expected, one of these plasma blobs was about to clip the Earth. And you can see the probability of the aurora was very high, and the aurora had expanded down to slightly lower latitudes. And I'll give you websites at the end. You can find out all the time what the probability of an aurora is wherever you are. Now, we measure how active the sun is by a number of ways. As I said, we always monitor it continually with satellites, both where we are at the Earth and to either side of the sun, so we can see what happens on the other side of the sun before it rotates into view. So that gives us an idea of what has happened that might release something in our direction. But you can also monitor how active the sun is on a long-term basis by simple thing, counting the number of sunspots on the surface. The more sunspots, the more magnetically active the sun is. And this has been done for about 4 centuries. And we know it goes through cycles of activity about every 11 years. We're going through this current sunspot activity cycle. So you're looking at sunspot activity on the vertical axis, time on the horizontal axis, and you can see we had a solar maximum, so that's when the sun is most active a few years ago, we've been going through a solar minimum, which has been fairly protracted. That means the sun has been fairly inactive. And as we come into next year, we're beginning to climb out of this minimum. I will just say though, the sun seems to be getting less active at the minute with time. Here's just in terms of the sunspot night or cycle, the activity of the sun with time. These are the last 3 cycles, and you can see that it seems to be getting slightly less active at each peak. So there may be a long-term trend in terms of the solar activity. But this doesn't mean that we're not likely to see the northern lights. At the minute, there are sunspots in the sun, so there are regions of activity. Some of you may have heard about a couple of weeks ago, so beginning of November, there was one of these flares, very bright flares seen on the sun, some plasma release, and that caused aurorae that were seen down on Norfolk and Bedfordshire in the UK, so seen at much southern latitudes. So be minded that these flares can happen at any time to get the more spectacular aurorae. Okay, so back to what's happening high in the atmosphere. So when you see aurora, they tend to be this, this very sort of green colour. And this is because, I mean, it's primarily oxygen in the atmosphere. Our atmosphere is made primarily of oxygen and nitrogen in the form of atoms and molecules and ions. And realize that the concentration, the composition, the density of the atmosphere varies with altitude. So the kind of aurora you get depends on exactly where the particles are being funneled into the atmosphere, where they're colliding, so what they're colliding with and how much energy are in those particles. So every aurora is just slightly different. Most solar particles come in at a height between 100 to 200 kilometers, and there the composition of the atmosphere is very different from what it is at ground levels. You've got nitrogen molecules, excited nitrogen molecules, you've got oxygen atoms that are abundant, high concentration of oxygen. So therefore, the kind of light you see most predominantly is from an excited oxygen atom. So you have a collision of the particle with the oxygen atom. This gives its energy to the oxygen atom, which would then release that stored energy 0.7 seconds later as light. Now, the reason this has to happen at 100 kilometers and above is that you can't have the atmosphere being too dense. If that happened down at the density of air that we get down at ground level, that atom wouldn't hang on to the energy for 0.7 seconds. It would be rapidly what we call de-excited by collisions with other neighboring atoms and molecules. It doesn't get the chance to decay naturally in the form of light. So you have to be at high altitudes for that oxygen atom to be unperturbed for long enough that it can release this light naturally from the original excitation, the original collision. So the kind of colour you see depends very much on what is being excited. Different molecules, different atoms have different energy levels, and so different energy levels are very give off very particular colours. So the most common is green because that comes from 100 to 150 kilometers K from excited oxygen atoms. But very often you see those green aurora are topped by red bands, and that's because you can also have a transition of oxygen where you get a red coloured photon. Now, this has to happen at much lower densities because the oxygen atom has to hang on to this energy for 110 seconds before it can use it naturally as a photon of light. So you only get this in the lower density regions of our atmosphere, talking about sort of 200 kilometers. And so you get the green lower down, and that's topped by oxygen atoms in the much sparser region of our atmosphere. You have a very intense bombardment of solar particles. You will see that some of the green aurora, those curtain, are fringed at the bottom with thin layers of purple light. And that's where the solar particles are so energetic that they've penetrated further down in the atmosphere, so to about 85 kilometers or so, and they excite nitrogen molecules to produce this sort of purple, pinky fringe right on the lower part of the auroral curtains. And then sometimes, more rarely, even higher up, you get above the green, the red, you get a sort of bluey purple band, and that comes from nitrogen ions that are high up, sort of 200 kilometers and higher in the air. And that's where you've got very rare, both it's not, the air isn't very dense, and you've also got ions rather than molecules of nitrogen. So you can see the variation in the aurora lights that you get depends on where you are in the height from the Earth, and where those solar particles are penetrating to, and what's at that depth of atmosphere to what they can collide with. So you get different colours. I will, though, just give you a word of caution that when you see, I mean, I'm showing you some fantastic pictures here, showing you the intense colours of the aurora. What you must be aware of is that when you see them with the unaided eye, they're not always that spectacular for a couple of reasons. One is that your eye needs to be dark adapted. So again, this is why it's good to be away from light pollution, ideally not to have a full moon in the sky. But the second thing is sometimes if you have a very faint aurora, the cells in your eye that pick up the light from faint objects where there isn't much light are the rods, and they don't have much colour sensitivity. So you might have an aurora in the sky, which if you took a picture with your camera, because it can gather light for much longer, it's picking up all the colours. When you look with your unaided eye, instead of this image I've got here, it might look slightly washed out version. I will say though, you do get, you can see much richer colours of the aurora. It depends on their intensity. So they're not always as vivid as the images and the videos make out. However, it's a much better experience in real life than it is just looking at these photos. I started off with a video that showed you various manifestations. So from what I've said and told you so far, let's look at some of those aurora, and you can get an eye into why they appear differently and what it is that you're looking at. So for example, I said in Southern Europe, if you see the aurora, it is most often this red glow. And that's because when you're far south, you probably, again, remember, curvature of the Earth, you're only seeing the top layers of the aurora. So perhaps the brightest part that you can see will be the red light from the higher oxygen and the excitation of the higher oxygen atoms. And it's low down in the north just because you're barely seeing it. If you move up to sort of mid latitudes and the slightly higher latitudes, that's it. Again, it can be just that general glow on the horizon, and you'll see the green, maybe the red, and you see more of the colours there. And as you shift north, that glow in the horizon actually resolves out into an arc. And that arc is where you're really seeing the auroral oval in, as it sort of circles around the northern pole. You're seeing it directly. And this can sometimes break up into, again, the more north you go, it can break up into ribbons snaking across the sky. Now, I will cheerfully admit that I plundered the web for most of the images that I'm showing you in this talk. This is the only photograph I took myself. I'm not very good at photographing the aurora because I tend to just stand there and gawp at them and forget to take any pictures. But this is from my last Hurtigruten cruise and one particular display. And what you're seeing here is we just had ribbons of green light from one horizon right round to the other, just lots of continuous ribbons. And what the images perhaps don't convey in the videos, because they're sped up, they don't convey. These do move and they change. And in terms of the height of these things, again, measuring them from the Earth's surface, these ribbons sometimes they change, so you can start to see rays here. Here's a picture that shows the rays a lot better. This is when these ribbons sort of develop into what we call curtains. And they've quite narrow. These ribbons and curtains are only about 100 meters thick, but they can be tens or hundreds of kilometers high and thousands of kilometers long. The rays, the striation you see within the curtains are because of the magnetic field. They're all parallel to the magnetic field, these vertical rays. So this means as you go more to the north, these rays are coming down almost directly above you, and they're overhead. And this is where you get some of the most intense aurora. It's when you're up in the Arctic Circle and you look up and the rays appear to converge because you've got the parallel lines of the magnetic field going way above your head. So the perspective gives you that convergence. And these are where you will see the most intense auroral displays. And that these move fast. You will see them spiral around, they'll flash and they'll flicker with different colors, and they are the most spectacular. So that's why it's more worth making an effort to go and see them rather than sitting and waiting for them to come to you in East Anglia or wherever you happen to live. Okay, I hope I've whetted your appetite. I'm expecting there may be some questions, but what I just have got here is a few websites that might be of interest. The first two, like spaceweather.com or spaceweatherlive.com, and they give you the current auroral oval. They'll give you indications of how active the sun is at the minute, how many sunspots, what's the likelihood of an aurora where you live, especially if you know, probably more relevant if you live somewhere in more northerly attitudes than us in Cambridge. And there are plenty of websites that give you fantastic and latest images of the aurora, but one that I always particularly enjoy is Astronomy Picture of the Day. Now, okay, admittedly, this is usually something to do with space and the cosmos, but they do generally feature any good aurora movies or pictures as well. So I'll leave it there. Very interested to see what questions you have, and hoping that you well, maybe you can also tell me about some of the aurora you might have seen yourselves. Okay, thank you very much.
Thank you, Dr. Carolin. So I'm just turning my camera back on. We've had some amazing questions, but before we get into those, wow, what an insight that you've given us there. I think the value of depth that you bring in terms of when, just relating that to when you're on a holiday with us, and that knowledge and that experience and that learning, and then obviously actually being able to see the aurora burst when you're having that experience, it's just incredible. And then to have you there really bring that to life, not only can you see it and clearly it's amazing, you have somebody there like yourself bringing it to life, as I say, just absolutely incredible. So thank you for all of that. I've been scribbling away, writing down all the questions that we've had. They're all very varied, actually. We've got quite a lot, yeah, lots of different ones. The first one that we have is a photo or a photography question, I should say. And you may have covered this slightly as you went further on in your presentation, but are the colours more vivid in slow exposure photos compared to the naked eye?
So yes, the colours are far more vivid in the images. I mean, if you have an intense aurora, you can see the colours of the eye. If it's very faint, your eye just cannot pick up the colour, and your camera shot will pick up a colour, and you take a picture of what you're looking at, it'll come out as green on the camera, and it'll be much more sort of grey in the sky. So yes, the images are far more vivid on the camera, but and I think you kind of alluded to this, when you are seeing an aurora, maybe this is just me, I'm so the experience is so different from just sitting there catching pictures on your camera. And this is why I'm hopeless at taking pictures, because the experience is what matters. There's nothing really compares to being under aurora and seeing it firsthand. So the fact that the images and the pictures are more vivid than what you see with the unaided eye doesn't detract from the experience at all. It is still awe-inspiring if you're lucky enough to catch them.
Yeah, when you showed that slide about the curtains, I mean, that's an incredible spectacle. And then you add in actually how far obviously the light has traveled and how long that light, it's just, again, mind-blowing stuff. On to the next question. So if there was a solar storm on a particular day, so let's say the solar storm happened today, how quickly would we see the light here in the UK? Would that land, or in the world, I suppose I should say, really, would that be pretty quickly, or would that take a period of time?
It varies a little bit. So the first thing, if there is a mass, what we call a coronal mass ejection, coronal mass ejection, if there's a really strong ejection of plasma from the sun, first thing we will know of it is a bright flash of X-ray light, and that travels at the speed of light. It reaches us 8.5 minutes later. The actual plasma, the bubble of plasma that might, that shot out into the solar system, first of all, it'll only affect us if it's shot out right from the face of the sun and travels directly towards us. Most of them are spat out away from the Earth or in other directions. But that plasma will take maybe a couple of days to travel from the sun to us. So this is one reason why we monitor the sun all the time with satellites. We catch these flares. That's why we look at what's happening around the other side of the sun, see if there's potentially active regions of the sun that are about to rotate into view that might release these bubbles of plasma. So it generally happens, as I say, 24, 36 hours later. Occasionally, it's faster. If you were anybody who was really paying attention will have heard me say that there was the Carrington event in 1859, where there was a bright flash of light in the sun and a storm. So in other words, that plasma hitting our magnetosphere happened 17 hours later. And in that case, there had been a similar event a week before. And if you have to realize the space between the planets and the sun there is gas there, it's not really a vacuum. But there'd been one of these discharges a week before, which more or less plowed through and cleared the gas out of the way between us and the sun. So when this second event happened, it didn't have so much interplanetary medium to plow into, and it arrived very quickly within 17 hours. But that's unusual. We usually have a few days' notice. So this is why it's, especially if you're ever in a position where you might be able to see the aurora, in terms of latitude on Earth, you just keep an eye on what's going on in the sun. And quite often they'll say there's been a flare in the sun, and they'll up the probability of the aurora the next night or the next 2 nights. So it's that kind of delay you're looking at.
Wow, thank you. Next one, how do the aurora australis compare to the strength of the aurora borealis? And are they seen, how far away are they seen from Antarctica?
Oh, now, I must admit, you are straying out of my zone of expertise, because I've only ever seen the Northern Lights. The southern aurora are exactly the same phenomenon. You're seeing exactly the same thing. It's just around the South Pole rather than the North Pole. And it's the same kind of latitude distribution. I've been showing you the auroral ovals. Every time there's a prediction, there's one for the north and there's one from the south. I think, again, it depends on the intensity of the activity. If the sun's very active, then that ring will expand and be seen outside of Antarctica. Of course, Antarctica is a fantastic place to watch aurora from, but slightly more difficult to get to, unfortunately. So again, it depends on activity of the sun. You can sometimes see them from New Zealand and outside of Antarctica, but again, I don't really know about that so much. Go and have a look at the auroral ovals and find out.
You can't know everything, Dr. Carolin. None of us can. I'm pleased to say I could quickly add to that Hurtigruten could take you to Antarctica. So I'm not going to miss an opportunity to sell you something. So please do look up those options as well, because we do Antarctica. We'd be very happy to take you there. Next one, we had a couple of questions on this subject, which was about a Carrington event. So if we had a very strong Carrington event, how would that affect things like satellites, computers, power cables, all those sorts of things?
It would be pretty awful. we have missed events like that, where a similar sort of discharge of plasma has been ejected and more or less passed where the Earth was a few days earlier. So we've had near misses, and sometimes we have them where they just glance the atmosphere. The Carrington event was a full face-on smack in the magnetosphere. Now today we'd be much more vulnerable. It's the kind of thing that would fry satellites, you know, the electronics and satellites, and we all know how we depend on satellites for, you know, GPS, navigation, telecoms. Again, this is one reason for monitoring activity in the sun, whether you can have the option, if you know an event is likely to happen, you can close down some of the more vulnerable satellites, the ones that are higher up, in, you know, less protected by the atmosphere, higher up ones, whether you can close them down and perhaps in some sort of safe mode for a while the storm passes. There are, of course, worries that if it's a very strong geomagnetic storm, it could affect power grids down on the Earth. So if we had an event like that now, I will say we are the kind of society we're in, we're much more electronically based, we've got satellites, as you said, we've got power grids, we're much more vulnerable than we would have been in 1859.
Of course, I mean, quite a thing to consider, really, isn't it? That in
Yeah.
it, all in itself. When those two questions came in, I thought, wow, you know, I mean, that's such a, yeah, that could be such a big event, obviously, clearly for us. Next,
I will say that one of the things that scientists, you know, I've talked about satellites monitoring the sun. What we're trying to do is to understand the behavior of the sun and, if you like, solar weather. The ultimate aim is to be able to predict where and when these events will happen. So not just observing, but be able to, I mean, I've talked about the solar weather and sort of 11-year timescales, but from day to day, it'd be great if we get to the point where we understand the surface of the sun well enough that we have much more notice of how likely these events are.
oh, fabulous, thank you. I had another couple of questions on the aurora occurring on other planets, and does that happen? And somebody also asked specifically and referenced Venus. And obviously with the magnetic fields, do we have much knowledge and understanding of what that would look like?
Right, I'm just going to share my screen with you again, if I may. Right, does that work? Can you see that?
Yes.
Right. Just in case this question came up, oh, come on. Here's a picture of Jupiter, an aurora on Jupiter. This is a montage where you've got a visible image of Jupiter, and superimposed on that around the North Pole, you have a picture taken in ultraviolet light, because the atmosphere of Jupiter is mainly hydrogen, so you have a difference of excitation levels, different atoms and gases involved, but you get aurora on Jupiter and also on Saturn. Here's some pictures just showing some aurora around the South Pole on Saturn. And it's interesting, you can see both of these, they tend to be a bit more sort of swirly than sort of a nice ring shape that we get on our Earth. So I'm not quite sure why that is. So yes, you do. I don't know much about Venus, I must admit, whether we see aurora on Venus, but it's basically any planet with an atmosphere and a strong magnetic field will generate an aurora.
Fabulous, thank you. I think you might have covered this one, but it was, do we know why the photos appear greener? So sorry, specifically I'll ask the question properly. Why do the photos appear greener than the lights to the human eye?
Well, it's because it's the way our eyes work. I mean, if you see an aurora, our eyes will see the green better than the red or the blues, because our eyes are most sensitized to green. It's the best thing. But the reason they appear paler is that you have, I mean, I'm not a biologist, so it's a very rudimentary explanation, but the kinds of cells, receptor cells you have in your eye, you have rods and you have cones. And cones work in bright light and see color very well. Rods work where you've got very faint light levels, but they don't have much color ability to differentiate color. So think of this, you know, if you wake up really early in the morning and there isn't much light, everything looks grey. But as more light comes, as the sun rises, colour begins to creep in. It's just this thing, it's to do with the light level. So faint aurora, you don't have enough light to trigger the cones and get that colour sensitivity. You're relying on these sort of colourblind rods. But if the aurora are bright enough, you get the cones kicking in, you see the colour, but the eyes particularly sensitized towards greens. That's where our eyes are most receptive, and so that's why they're easiest to see. However, it's worth saying that green is the most common, is the strongest colour anyway in the aurora, because that's the energy release from these particular oxygen atoms that are at the sort of prime height where the particles come in. So it's a combination of the eye that also being the most common colour.
Fabulous, thank you. Some great questions about, do we know why the solar cycle is 11 years? Or every 11 years?
It's very complicated, but it's to do with reversals of the magnetic activity within the interior of the sun and the way the poles will sort of switch around. It'll get more and more knotted and then released and switch around. So it's to do with the sun's interior and the way it generates magnetic fields. And to talk about it properly would take a lot longer, but we have ideas about why it is. Probably not an innate understanding, but it's something that's been observed for a long time, and it tells us something about what's going on within the interior of the sun.
Fabulous, thank you. I'm conscious that we're getting towards the end, so we're going to I just need to check a few that have come in while we've been talking. This one, when was the last period of sun inactivity?
Well, I'd say about the last 3 years, actually. There was a graph that I showed. The sun has, I would say, almost like the last 20 years, it's been really disappointing. Last 15 years, it has not been as active as it used to be. And I know I just mark this basically from the point that I bought myself a solar telescope. So this is a special telescope which makes it safe to look at the sun. I hasten to add, you don't use an ordinary telescope for that. And the sun's been really boring ever since. It's still going through its cycles, but we've gone through the most recent minimum and we're just climbing it out of it now. There are periods, there's something called the Maunder minimum, which back in the 16th, 17th century, I can't remember, so probably about 400 or so years ago, where the sun was very inactive for a couple of decades and there was barely no sunspots seen. Now, we're not as bad as that, but we are going through a period where the sun is relatively inactive. So that's bad news for the Northern Lights. It's good news for satellites and our technology.
We had a question, he says, and this sounds like a whole other presentation. I may be wrong to say this, but are you able to discuss the Steve aurora?
Steve aurora.
Yeah, Steve aurora. It was something that I knew, so I wasn't quite sure if that would mean anything to us or not.
I don't know.
Fine,
I don't know the context.
say.
I'm sorry, whoever asked that question. I'm not quite sure what you mean there.
Next one, what are the particles that come from the sun?
It's mainly helium ions, protons, electrons, just, you know, charged, most basic. You think most of the sun is hydrogen, and when hydrogen atoms get ionized, you get protons, you get electrons, and that's the primary particles that are streaming in and hitting our atmosphere.
Fabulous. I really like this one in particular. What do you think of the theories of the auroral sound? And does the aurora make sounds that humans can hear?
Okay. This is a slightly confusing issue because as well as releasing energy as light, the aurora also produces intense radio emission. And this is because whenever you have a moving charged particle spiraling or accelerated around a magnetic field line, which is what is happening when this stuff is coming down into the Earth's atmosphere, you've got magnetic fields going around charged particles going around magnetic field lines. They're getting accelerated and they produce radio emission at very low frequencies. So you get this natural radio emission, and you don't hear it as such, but you can go to places like the European Space Agency where they have sonified that. So change it from radio signals to a sound that you can hear. And it's like a very sort of scratchy, squeaky, chattering radio signal. So if you're interested in that, I urge you to go to the ESA website and look for that. I don't think, I mean, there are allusions to people hearing sounds from meteorites coming in, but I haven't heard of people actually hearing sound from aurora. So again, the only sounds I'm aware of are where it's the radio signals that have been sonified and made into sound so that we can appreciate them. And what is interesting there, I will say, is that they change into sound, but the variation in the sound is the real time. It hasn't been sped up. So it gives you an idea of how fast the aurora are changing just from the changes in sound.
Fabulous, Dr. Carolin. Thank you ever so much for answering all those questions. I'm conscious that we're now past our sort of 8 o'clock deadline. We have answered most of the questions that have been submitted, and I'm sorry that we've not been able to get to every single one of them, but I think we'll be here till quite late into the evening. So on my part, I would just obviously like to thank you all for attending today's presentation and talk. I hope you found it really informative. I hope it's fueled your thirst for more information and knowledge, and of course, and that will then naturally turn into coming to travel with us at Hurtigruten Expeditions or Norwegian Coastal Express. Clearly, we have a fabulous tour that's on sale that you can join, that Dr. Carolin will be on, as we've already mentioned. And as I say, it would just be absolutely great to have you experience it in real life, because it is just breathtaking. It really is a wonderful experience, very much a bucket list experience. So thank you very much to Dr. Carolin. As I say, I don't think Claire had wanted to sign off or had plans to, but now I've kind of said that, she's probably potentially scrambling to unmute herself. Here she is. I can see she's unmuted.
Oh, I think you've said everything. Thank you very much, Russell, and thank you everyone for joining. Our next event will be on the 14th of December, and the information will be available on the Cambridge and Oxford websites, hopefully at the beginning of next week.
Fabulous.
So
Thank you.
Thank you. So I think we're all done. Thanks very much.
Thanks once again, everyone.